I've changed the format of the announcement slide slightly because we've got so much going on. I thought maybe it would be simpler to show it to you in terms of deadlines instead of the individual elements that there are. So today, you've just submitted homework 3B. In lab today, you're going to be submitting your response for Water Gems 1. And so I'll take that at either 2 o'clock or 3 o'clock, depending on which lab group you're in. And then the lab experiment we're going to be conducting is the buoyancy experiment. And I thought I printed out the handouts, but I don't see them here in my stack, so I'll just give them to you in the lab. It's actually a very simple experiment. It shouldn't take too much time, like none of our labs do, at least none yet. So we should easily finish within the hour that we've got allotted for the buoyancy lab. Next Tuesday, you've got a lot going on. Lab report 5 is due, so that's the lab report that goes along with the buoyancy experiment we're doing today. And that's due by 11 a.m. because next Tuesday is our midterm exam. And to give you more time on the midterm exam, we're switching when we do the lab and when we do the class part of the day. And so ordinarily, you know, we've got a 3-hour window that we can do lab, and our class lecture is just 75 minutes. But what we'll do on Tuesday the 30th is we'll do the lab during our 11 o'clock to 12:15 time slot, and then at 2 o'clock is when we'll take the midterm exam. And I won't let you take the full 3 hours. I'll let you take 90 minutes for the exam. For that exam, you're allowed to bring an equation sheet that includes equations and equation definitions. The equation sheet should not include step-by-step instructions on how to solve problems. That understanding should be in your mind. And I'll collect the equation sheets along with the exam when you're submitting it. The homework assignment that's also due on Tuesday, so you've got a lot going on Tuesday. A lab report due, a homework assignment due, and a midterm exam. And I'm going to make you do 50 push-ups. No, the last one, that's a joke. But on this homework assignment, the course schedule that I gave you at the beginning of the semester, I must have had I mistyped something because it says 105, 105, 117. You don't have to do problem 105 twice. You need to do 105 and then 107. So that's the updated problem set. You may want to change your course schedule if that's what you've been relying on. But that'll be due at 2 o'clock, which is when we'll begin the exam. We'll talk a little bit more about the exam on Thursday, but I wanted to mention the switch in times because that's really important that you be ready for the lab and have your lab report submitted at 11, and then we'll do the exam at 2. Any questions about these announcements? Okay, so today we're going to finish hydrostatic forces on curved surfaces and actually begin talking about buoyant forces. We'll continue talking about buoyant forces because I gave you an email hint on how to solve one of the problems. Okay, before we begin this slide, I wanted to do a drawing just to review the concepts of forces on curved surfaces. So here we have the water surface. We've got a curved gate. Okay, we've got it coming into some sort of a wall here, going into a wall there. And so we can see very clearly that this is a quarter circle. When you're finding the forces on a gate, then it's the vertical forces and the horizontal forces. And so you break it up into the individual pieces and you say, the vertical forces are the weight of the water that's above the gate. And how do we calculate the horizontal forces? Well, the weight of the water is based on the volume times the unit weight. So that's the vertical forces. But what about the horizontal forces? Okay, it's the hydrostatic force on what? On the projection of the curved surface. And so you have to think about what sort of a shape is the projection making. On the problem where it was a bolt that was plugging a hole from the homework, the shape it was making was a circle. That was the vertical projection of that surface. So we can have a gate that's shaped like this, or we could have the gate shaped a little bit differently. It could be shaped like that. Now that's a little bit trickier to find the volumes, right? So let's just talk in terms of problem-solving strategy. If it is shaped like this, how do you find the weight of that water? How could you find the volume if you don't have a formula for that particular shape? Okay. Right. So you break it up into pieces. You say, it is a square. I'll subtract out the quarter circle, and what I'm left with is the actual water that's above the gate. Exactly. So that problem-solving strategy will allow you to do a lot of bizarre shapes that you may not have specific formulas for. And so that works for the volume. It also, that same approach works for the center of area. And that's what example we were working through on Thursday when we were finding the centroid for that piece that's left over. And then I showed you a slide last time that talks about what if we have a tank that's like this, and it goes sideways. So here's the tank. All right, if water is up here, obviously it's going to start gushing out all over the place. But if we put a cap on that opening, so if we put in a gate here, so we put in a gate, then we can find the forces that are acting on that gate by the weight of water that would be above it. So what we can do is we can say there's some hypothetical water surface that there would be, and so we can find how much water would be above that gate. That's one approach. The other is to find with delta H. We can find the pressure here. Pressure is delta H times gamma. And so then if you know the pressure and the area, then that'll be a force that's pushing up. Some methods, you know, the one approach of finding the weight that would be above it is better if it's an irregularly shaped object. And you can't find the pressure at a single spot because maybe that gate is curving and it has different depths. But either one of them ultimately will give you the same answer. And it's this idea that kind of guides the ideas about buoyancy that we're going to be taking a look at today. So let's take a look at a couple of pictures. These are some photos. Boy, we really need a new projector. It's just almost can't see that. Well, you've got the slides there in front of you, right? Oh, but it doesn't have this pictured, right? Okay. This is a gas station. I wonder if I can turn up the brightness on the screen. Let's see. Menu. This may not help. It'll probably just make it all washed out. We'll see. Is that better? It looks the same. Oh. Okay. There's something poking out of the gas station there. What is buried at a gas station? Dinosaur eggs. Submarines. It's the fuel tank is underground. It's buried underground. And so why would a fuel tank all of a sudden unexpectedly break through the concrete? And here's another picture of it. Hopefully it's a little bit brighter. Slightly. Why would... Okay, the tank floated out. So if we do a little diagram of, here's the ground surface. Ground surface. Okay, if we go deep enough, we get to rock. So here's rock. And above, in between the surface and the rock, is the water table. And so down here, the soil voids are saturated, meaning that obviously soil is a mixture of solids and empty spaces. Underneath the water table, all of those empty spaces are full of water. So the soil is saturated. Above this, the soil is dry. And that's not quite that simple because even dry soil has some moisture that's attaching itself to the soil grains. But a tank that is full of gasoline is going to be pretty heavy. So it's going to have a lot of weight, and it's not going to all of a sudden crash out of the concrete. if it's really rainy and wet, this water table can rise. And so if the water table rises above the tank and it's full, we're still okay, because there are going to be some buoyant forces. F sub B, just like a boat will float in the ocean, it has buoyant forces. Anytime an object is displacing water, like this tank is pushing the water out of the way that otherwise would be there. And so there's a buoyant force acting upward in the magnitude of the weight of the water that's been displaced. But the tank is made out of steel, it's full of gasoline, and so most likely the weight of the tank exceeds the buoyant forces. But what if that gas station is out of business, and so now it's just an empty tank with no fuel in it, and the water table is really high? Well, then the buoyant forces might exceed the tiny little weight of the tank, and then it can come crashing through the concrete unexpectedly, like an emerging submarine out of the soil. So that's what happened here. Actually, this is an old filling station in Charleston that was out of business. The water table rose, and the buoyant forces pushed that fuel tank up out of the ground. And being able to visualize the forces and kind of conceptually understand what happened here will give you a big leg up on understanding the rest of buoyancy. Let me see if I can find this buoyant video. There we go.
Oh, those are Maui seconds. Oh, there he is. Shoot! Oh! Red October.
The audio adds a lot.
Oh, those are Maui seconds. Oh, there he is. Shoot! Oh!
Okay.
Red October.
Why was the submarine underwater and staying underwater before this video started? Because it's not like that submarine was built at the bottom of the ocean and then they released it and it instantly floated to the top. It was underwater in equilibrium for a while. When it was underwater in equilibrium, why is that and how is that possible that it was in equilibrium and then all of a sudden it floated to the surface? What do you think? Here's our submarine. Oh, the conning tower with the fins. All right. So when it's in equilibrium, what do we know is true when it's not moving upwards? It's in some sort of a balance. And so the submarine has a weight that's acting downward, and the buoyant force is acting upward. And so when it comes out of equilibrium, when it's rising, then what is, okay, so I'm going to say equilibrium means the weight is equal to the buoyant force. When it was rising, so rising, then we know that the buoyant force is greater than the weight. So how do they make that possible? Do they increase the buoyant force or do they decrease the weight in order to get the submarine to rise? Okay, so how do they decrease the weight? If it's like a submarine made out of metal and there's people inside, they make people swim out, you're out of here, we need to rise. Water? Okay, that's exactly right. They, in a way, you can think of it as they're capsizing part of the boat intentionally to make it rise and fall. There are pumps inside of submarine, and so there are these tanks at different places in the submarine where they keep a certain amount of water. You can just think of it as like a little mini swimming pool, although probably nobody's in there swimming laps. It's just these enclosed tanks, and so when they want to sink, they'll fill the tanks up with water, and so all of a sudden now the weight is larger than the buoyant force, and it's going to start sinking downward. And then when they want to surface, they'll pump the water out, so they'll pump the water out, and then the submarine weighs less and it begins to rise. In fact, the Navy submarines, they sometimes want to be able to surface very quickly, and so they have really high pressure air so that they can just blast the water out of these tanks and quickly have a big change in the weight versus the buoyancy. So the buoyancy force is fixed. They're not going to be changing how much the water pushes up, but they are adjusting the weight of the submarine. And so what about getting the submarine to sink? So sink is when the weight is greater than the buoyant force. Okay. Now, let's start from the video. There's one more thing I want to ask about.
Oh, those are Maui seconds. Oh, there he is. Shoot! Oh! Red October.
Why did it stop? How come it didn't start floating into the atmosphere and then towards the moon? It reached equilibrium at the surface. All right, so let's draw a drawing here of equilibrium at the surface. Okay, so here's the submarine. Here's the propeller. Really important that I put that in the drawing. So when it's at the surface, it's in equilibrium again, and so the submarine has some weight acting downward, and there's some buoyant force acting upward. And so how submerged the submarine is, it's only partly submerged now. The amount that it's submerged tells us how much the submarine actually weighs. And that's one way that you can find out the mass of an irregularly shaped object is you can see if it floats and how much does it float and what's the volume of water that's displaced. You have a couple of homework problems that take that approach. They tell you about how something that's buoyant, how much it's floating. And you can use that information to calculate how much it weighs. All right, so let's talk about this. The buoyant force, the key thing here is the volume of water that's displaced and how much that volume of water would weigh. Basically, today's entire lecture can be summarized by F sub V, B, is equal to V times gamma. So this is the buoyant force equation. The volume of water displaced by whatever this object is multiplied by the unit weight of the liquid. And so if it's a submarine, we can find out how much water does the submarine push out of the way by virtue of the fact that some of its hull is beneath the water line. If you know how much water it pushed out of the way, that's how much the water is pushing upward, the weight of that water that got displaced. And that's what we're going to see in lab today, is we're going to see a little floating boat, for lack of a better word. It's really just a box. We're going to see a floating box, and we're going to load some weights into it, and it's going to sink down into the water a little bit. It's not going to sink to the bottom. It's just going to sink a little bit until it comes into equilibrium, and the amount of water that it pushes out of the way when we add those weights into the corner of that box is equal to the weights that we add to the box. And so it will be this floating rectangle here, and it's only floating a little bit at first, and then we're going to add some heavy weights into the corners, and then it's going to sink down into the water. And so I'm going to draw that as the water line is higher up on the edges because it's displacing more water in order to overcome the additional weights that have been added. It comes into a second equilibrium. So think about a submerged object, irregularly shaped. The hydrostatic forces are acting on it from all directions. You've got pressure acting normal to the direction of the surface, and so it's showing that the pressure on the bottom of the object is bigger than the pressure at the top of the object. The reason for that is because the bottom of the object is deeper down in the water, and so the pressure forces obviously are going to be greater because delta H is greater the lower you go in the tank. And so the underside of the object, the pressure is higher down here. And that's because it's deeper. So here's that object, and consider it in terms of the volume of water that's above it, the volume of the object itself, and there are external forces acting on the object. And a force we already know, is pressure times area. And so that if we were to integrate the pressure over lots of little areas, if we broke this irregularly shaped object into little 1 centimeter squared surfaces, and we found out how much pressure is acting over this one little square centimeter, and the pressure times the area of that square centimeter, and then added them all up, we could find out the forces, and we could find out the net forces between the two. It turns out that the upward forces, the forces that are pushing up on this object, are equal to the volume of the object itself and the volume of water that's above it multiplied by the unit weight of water. The downward forces is just the weight of the water that's above it, and so the difference between the two is called buoyant force. It's where you say the net difference between the upward and the downward forces, and that's calculated by the volume of the object. Here it's saying this object is B, multiplied by the unit weight. Any questions so far? So how do you know if this object is going to float or sink? What if we're holding it in place right now? I'm holding it in place. I'm going to let go. And what's going to determine if it goes up, goes down, or stays where it's at? It's the density object relative to the density of the fluid. And so if this is water, and if the object has the same density as water, if the object just coincidentally had a density of 1,000 kilograms per cubic meter and I let go, it's going to be neutrally buoyant. It's just going to stay right there. If the object is made out of steel and it's more dense than water, I let go, it's going to sink to the bottom. If it's a plastic cube and the density is less than the density of water, it would float to the surface. Yeah?
Neutrally buoyant. If you place it anywhere at any depth, is it just going to remain at that?
Yeah. Because the density of water doesn't change as a function of depth. Density is constant. So what they try to do in the case of the submarine is they'll get it neutrally buoyant, and then they steer up and down as they desire with the, what are those called, ailerons on the side? Any submariners in here? No? I think they're called ailerons, but they get it neutrally buoyant, and then they can go up and down just by using the fins on the side. All right, so let's do a calculation example here. Let's take a look at the density of a plastic cube. It's 1 meter by 1 meter by 1 meter, and we're going to prove to ourselves that it's as simple as this difference in the forces. And so we're going to take a look at the force on the top of the object, the force on the bottom, and then the difference between the two. As it says in the drawing, it's submerged at a depth of 3 meters to the top of the cube, and then we're going to find the force on the top and the force on the bottom. So the force on the top is going to be the pressure at a depth of 3 meters multiplied by the area of the top of that cube. Okay, so we've got 3 meters of water, so 9810 newtons per meter cubed, and the top area is 1 by 1, so 1 square meter. That gives us the force is 29,430 newtons. And that's saying here we've got a cube, and the equivalent hydrostatic force acting downward is 29,430 newtons. Okay, and we'll find the force on the bottom by the pressure at the depth of 4 meters, because the bottom of that cube is 4 meters below the surface times the area. So it's 4 meters of depth times 9810 newtons per meter cubed, and it has an area of 1 square meter. And so that is 39,240 newtons. And then the difference between the two, okay, let me draw that. So here we had 39,240 newtons acting upwards. And so the difference is 39,240 newtons minus 29,430 newtons is equal to 9,810 newtons. And so coincidentally, no, not coincidentally, if we were just to say the buoyant force is the volume displaced multiplied by the unit weight of the liquid, well, this is a 1 by 1 by 1 cube. And so the volume displaced is 1 cubic meter, and the unit weight of the liquid is 9,810 newtons per meter cubed. And so the volume times the unit weight should tell us that 9,810 newtons per meter, 9,810 newtons is the buoyant force. So buoyant force means the difference between the forces pushing up and the forces pushing down. So if we let go of this, it should float to the surface, because it said here that the weight is negligible. It must be a really, really lightweight plastic for it to be considered negligible. Okay. Now this is showing a partially submerged object, and how deeply it's submerged depends on the volume that's underneath the water surface. And so this is another one of those classic mistakes that I'm always telling you, that it's easy to get tripped up on a certain thing. The volume of the object is sometimes given to you, but it's only the volume that's under the water line that determines what the buoyancy is. And so here, it would be a trick if they told you the volume of the object and then you're trying to find the buoyant force based on the volume of the object, because it's only this volume that's under the water line that accounts for the buoyant force. So to illustrate that, I'd like to have you work either individually or with a partner to go through each of these 5 steps and determine, based on how it's floating, what is the buoyant force, what's the weight of the block, and so on. What we know is that this block is 10 meters wide, 10 meters long, meaning 10 meters into the page, and then the total height of this face is 5 meters. As you can see, the dimensioned distance of 4.6 meters is referring to from the edge to the water line. So this isn't fully submerged. This is only partially submerged. And so you can learn a lot about this object by the way that it floats. Just like we know a lot about an iceberg by the way that it floats. You know, they can estimate what's the total volume of an iceberg based on how much of it's sticking up out of the water. This is a similar idea to that. So I'll turn you loose to work on that with a partner or individually, and meanwhile I'm going to hand back some assignments and things that I've got to give to you. So it's a 500 cubic meter block, which is enormous, and we could land helicopters on this big piece of plastic if we needed to. It has a buoyant force, though, that depends only on the volume that's underneath the water line. And so we need to find the volume displaced by multiplying 10 by 10 by 4.6. So that gives us 460 cubic meters of displaced water. That's the water that's pushed out of the way by that block being there floating around. Multiply by the unit weight, and we get 4.51 million newtons. The weight of the block is equal to the buoyant force since it's in equilibrium. It's floating there, and it's not continuing to rise. It's not sinking. We haven't taken a snapshot of it as it's moving. It's in equilibrium, and so the weight and the buoyant force are equal. The volume of the overall block is not just how much is under the water line, but it's at the overall dimensions. Turns out to be 500 cubic meters, and then that was just sort of setting you up to find the unit weight or the specific weight of the block. Now sometimes that's a little bit weird to think about something that we'd normally associate as a fluid property with something that's a solid. But there's no reason why you can't talk about a specific weight of a solid like this. I mean, a solid can have a density, so a solid could have a unit weight or a specific weight, and this one does. We can calculate the weight of the block divided by the volume of the block. So it's 9025 newtons per cubic meter. And that makes sense that it's floating, because if it had a unit weight more than water, it wouldn't be floating as shown. But it's less than water, and so it's floating. But the other thing we can do is calculate the specific gravity, which is just the ratio of the unit weight of the block to the unit weight of the water. So why is it floating this much under the water? Why isn't it floating, like here's the water, why isn't it half and half? Why isn't it 2.5 under the water line and 2.5 above the water line? Why is it just peeking out a little bit like this? Okay, so you noticed a trend. It's not a coincidence that you could say the specific gravity is 92% of water. What percent submerged is it? It's 92% submerged. And so the unit weight and the percent submergence has a relationship there. So that if this had a specific gravity of 0.5, that would mean we can expect it to be 50% submerged as it floats on the water surface. If it had a specific gravity of 0, it would just be in contact, just the surface would be floating there on the very top. Of course, there's no object that has a specific gravity of 0, but it was a very, very lightweight, like if it was hollow instead of solid plastic. You know, this is solid plastic. Well, what if it was hollow? It's possible that it might be just only a very thin depth of it submerged and the rest of it up out of the water. Any questions about this?
How would you find the specific gravity of an object if it was hollow? You have the
Right. Yeah, so if it was a mix, so that would depend on how, like the wording of the question. Because they could make a really tricky question, and they could say, so you've got water and you've got a plastic cube. But let's say it's partially hollow, like it's partly plastic and partly air. So here's the air and then here's the plastic. So then you got to be really careful on how the wording goes, because then you need to look to see, are they saying what is the specific weight of the object overall or of the material? So this is plastic, this is air. So did they say what's the specific weight of the cube? And if it's of the cube, then you just do the same thing that we just did. You just only have to look at what's underneath the water line, etc. But then if they said what's the specific weight of the plastic, then you'd need to say, all right, well, I've got a certain mass of plastic here and I've got a certain air volume, and you'd need to subtract the air volume from what's being displaced. And so it would be a little bit more involved if they just wanted to know the unit weight of the plastic rather than the unit weight of the object overall.
What if it's like that and the unit weight of the material is higher than water, like on a steel ship?
Right. Yeah, so why does a steel ship float if the unit weight is higher? Here's our cruise ship, the SS Good Times, all right, and so on, etc. Why, if it's made out of steel, why is it not sinking? It's because you just need to find out the volume underneath the water line. So the buoyant force is equal to the volume displaced times the unit weight of water. So all of that water that is pushing out of the way is equal to how much it weighs, even though it's made out of steel. And the individual components don't have to be lighter than water in order for the whole to float. You can have the individual components way more as long as there's some empty volume there. Now, if it was full of, like if they filled it up with steel, in addition to being made out of steel, then it wouldn't float anymore. So you can only, like the coal barges that you see going down the river, those are pretty low to the water. But the reason why it floats is that the coal has a density that, even though the density of the coal is greater than water, here's the water, here's the barge. Probably they only fill it up this much, and then the other thing to keep in mind is that there's some voids there. Here's a big pile of coal. So even though one individual block of coal is more dense than water, the reason why the barge floats is that all of the volume that's pushed out of the way by the barge exceeds the weight of the load that the barge is carrying and the metal of the barge's weight. And we'll get actually to see the little floating pontoon that we're working with today is very similar in shape to the barges we see go down to the Ohio River. Good questions. Any other good questions? Okay, so this is that figure that I've shown you before and referred to at the beginning of the class today. You can find the force that you have to push up in order to keep that plate in place. It's equal to the weight of the water that's above it. And by the same token, you can find out the force that you need to push down on this gate because it's equal to the weight of the water that would be above it. It's pushing water out of the way, essentially. This gate is preventing the water from rising to this level. And so the overall force required to hold it steady is equal to the weight of water that it's displaced. Okay, here's one more complicated example that we're going to take a look at today. We've got a floating wooden block that's partially submerged, and it's connected to a metal object that is fully submerged, and the density of the metal is greater than the density of water. So this metal would sink to the bottom of the tank except for the fact that it's connected to this wooden block. And what we know about the block is its dimensions. It's 10 millimeters by 50 by 50, and we're given the specific gravity of the block. We know the volume of the metal object, and the key to solving this is looking at what is the buoyant force acting on these two different objects. It's related to the volume that's displaced in both cases. So we're going to go through and find out the tension in the cable and the mass of that object. And the way that we'll do it is by going through some steps. We're going to find the buoyant forces, then the weight of the block, and finally a force balance will tell us everything else that we need to know. Okay, so first of all, we know that the wood has certain dimensions here, so we're going to calculate the buoyant forces. First of all, the buoyant force that's acting on object 1. The object 1 is the one at the top. It's the wooden one. So F sub B on object 1 is the volume displaced by object 1 multiplied by the unit weight of the water. Okay, object 1 is only partially submerged. It is 7.5 millimeters by 50 millimeters. By 50 millimeters. Okay. Now the unit weight is given in terms of newtons per cubic meter, 9810 newtons per cubic meter. Since we've been working with millimeters here, we're going to convert from cubic millimeters to cubic meters. There's 10 to the 9th millimeters cubed in every meter cubed. And so if we divide by 10 to the 9th, then it'll convert this volume into units of cubic meter, which is what we need. So the buoyant force acting on object 1 is 0.184 newtons. That's the force that's pushing up on object 1. Now, even though object 1 is connected to object 2, we don't even have to know anything about object 2 to know what the buoyant forces are on object 1. It depends only on how much is object 1 submerged. So that's the buoyant force on object 1. Now the buoyant force acting on object 2 is going to be, as you might expect, the volume displaced by object 2 multiplied by the unit weight of the liquid that it's displacing. We're told that object 2 has a volume of 6,600 cubic millimeters. And so that will be 6,600 cubic millimeters divided by 10 to the 9th cubic millimeters per cubic meter. And that tells us that the volume, then we have to multiply that by the unit weight, 9810 newtons per meter cubed. Okay, so the buoyant force acting on object 2 is 0.065 newtons. And that's also acting up, the same as buoyant force 1 was acting up, towards the surface. What do we know about the weight of the block? We're given its specific gravity, and so the weight of object 1 will be the specific gravity times the unit weight of water times the volume of object 1. Okay, specific gravity times water will tell us what's the specific gravity of the block, and then we'll multiply that by the volume, the overall volume, not the submerged volume. So that's 0.3 times 9810 newtons per meter cubed times the 10 millimeters by 50 millimeters by 50 millimeters. And then converting from cubic millimeters to meters, it's 10 to the 9th cubic millimeters per cubic meter. Okay, so the object 1 has a weight of 0.0736 newtons. We can't find the weight of object 2 yet. All we know is that it's metal, so it's probably going to have a density greater than water. I can't think of any metals that are less dense than water. But we can do the force balance. Let's take a look at the force balance on the block. Okay, so here's object 1. This is object 1. And it has a weight that's acting downward. Here's the weight of object 1. And there's a cable pulling it down. So I'm going to say the tension in the cable is pulling down, and then there's the buoyant force, F sub B, on object 1 that's acting up. Now, I should have drawn them on top of each other because they both act through the centroid, but I've shifted them sideways just to make it easier to see that there's two different things there. There's the T and the FB, but they're actually on top of each other if we're wondering about like the alignment of where those forces are acting. It's through the centroid. So the force balance here, as you can see, is that we've got F sub B 1 is in equilibrium with the tension and the weight. We know two of those three. We know the buoyant force and we know the weight of object 1, so we can find the tension in the line. And that tells us that the tension is the buoyant force from object 1 minus the weight of object 1. That is 0.184 newtons minus 0.0736 newtons. So the tension is 0.1104 newtons. Is everybody with me so far? Have any questions about this? So we can do a force balance about the metal object now. Now we've got this piece that's underwater, and what we know is it's got some tension that's lifting it up, the tension in the cable. There's a buoyant force pushing upward that depends, the buoyant force depends on the volume of this. And then there's a weight acting downward. And that's the weight of object 2. Okay. In equilibrium, everything's going to be balanced out. So the weight of object 2 will be in equilibrium with the tension plus the buoyant force in object 2. So if we want to know the weight, it's going to be 0.1104 newtons plus 0.065 newtons. That the weight of object 2 will be 0.1754 newtons. Okay, now this example asks us to find the weight of the block, which we did, perform a force balance, and then we want to know what's the mass of object 2. Like how many grams is it? We know the weight of it, and so the mass of it is just going to be, mass of object 2 is weight of object 2 divided by g. So it is 0.1754 newtons divided by 9.81 meters per second squared. Okay. If we remind ourselves what is a newton, that is 0.1754 kilograms times meter per second squared divided by 9.81 meter per second squared. So that's going to cancel out. The meters per second squared is going to cancel out. All we'll be left with is that it's 0.0179 kilograms. In other words, that's 17.9 grams is the mass of that metal piece. You've got a really tricky homework problem that is kind of like this, because there's a cable and there's a weight. I'd like to show you a little, give you a sneak peek of that homework problem, but before I do, are there any questions on this example? All right. Anybody have a copy of the textbook with them today? I could probably do the drawing by memory, but it's better if I look at the picture. Thank you, Isaac. Okay, the problem I am thinking of there it is. It is 3107. That's on your problem set. So what we've got is ground level, a hinge that's attached to a gate, a stop, cable, a pulley, here is the water line, and it's connected to concrete. Okay, so here we've got some water, and so they're asking basically how much concrete is required, the minimum amount of concrete required to keep the gate closed. And so we know that the hydrostatic forces, thank you, are trying to open up that gate. So we've got water pushing this way. If this concrete block wasn't there to hold this hinge, then the hydrostatic forces would push this gate down and the water would just spill everywhere. But if we pull on this, then obviously, you know, it's causing a force to resist the hydrostatic force. So here's our hydrostatic force, F sub h. And so you're going to have to find the magnitude of the hydrostatic force and its location, YCP, and do a moment analysis about the hinge. And so you're going to say, well, I've got a hydrostatic force at a certain distance. Now you'll know the distance there, and you'll know the magnitude of the force, and so that is causing it to turn clockwise, and then the force required to hold that steady is going to be the tension in this cable. So you'll find the tension in the cable by doing the hydrostatic force balance and the moment analysis about the hinge, but then now we're working with, here we've got a concrete block, and it's underwater, and so you know what the tension has to be. What are the other forces in play? Okay, there's buoyant force. And what else is there? There's the weight of the concrete. Both the buoyant force and the weight depend on the volume of concrete. And so what you're going to have to do is you're going to say the buoyant force is up, the tension is up, and the weight is down. So the tension plus the buoyant force are going to equal the weight. And what's the formula for buoyant force? It is the volume displaced times the unit weight of water is going to equal the weight of concrete. And the weight also depends on the volume of this block, whatever it is. Instead of saying volume displaced, I'm going to say the volume of the block, because it's this concrete block that's displacing the water. Block. And here it's the volume of the block. And then it is going to be the unit weight of the block. So here's the tricky thing is we're talking about the unit weight of a solid, not the unit weight of the liquid. There's two different unit weights. In order to find the weight of that concrete block, you have to ask yourself, you know, what's the unit weight of the concrete? I think they give you that. So the only unknown, since they give you the unit weight of water and of concrete, and you will have previously calculated the required tension in that line, the only unknown is going to be what's the volume of concrete that's required. So I like it because you know, you have to do this analysis over here. It refreshes your memory about hydrostatic forces, calculating YCP, moment analysis. You do all that foundation work, and then you move on to the buoyancy question. It's 2 in 1. 2 great problems for the price of 1. I will see you at 2 o'clock or 3 o'clock, depending on which lab group you're in. We will start the lab and have a great time observing buoyancy. So have a great day, and I'll see you then.